There is a moment, if you have ever been alone in a large open space at night, a field, a rooftop, a stretch of empty beach, when you look up at the sky and feel something that is difficult to name precisely. It is not quite wonder, and it is not quite fear. It is something in between. A sudden awareness of scale. A sudden sense that the darkness above you is not empty in the way a ceiling is empty. That it goes on in ways the mind cannot fully process. And that what might be out there in all of that depth is genuinely unknown. Most people have that feeling once or twice and then move on. They go back inside. They check their phone. They let the ordinary world close around them again. But some questions, once you actually look at them directly, do not let go that easily. Here is one of those questions. What if that feeling, that sense of being watched, of being observed from somewhere in all that darkness, is not just a psychological response to vastness? What if it reflects something real? Not in a mystical sense, not in a supernatural sense, but in a genuinely scientific, physically grounded sense. What if the question of whether Earth is being observed right now is not a philosophical speculation, but an empirical question with real evidence on both sides? That is what we are going to explore today. Not with certainty, because the honest answer is that certainty is not available yet, but with the full weight of what science actually knows, what it suspects, what it cannot explain, and what it is actively investigating. We are going to go through the physics of observation across interstellar distances, the specific evidence that suggests something might be watching, the institutional acknowledgements that have quietly shifted in recent years, and the scientific frameworks that take this question seriously at the highest levels of the field. By the end of this conversation, the question will not feel like science fiction anymore. It will feel like exactly what it is, one of the most serious open questions in contemporary science. Welcome to Brain Twist. If this is your first time here, this is where we take the biggest questions in space science and follow them all the way to where they actually lead, without shortcuts and without sensationalism. Subscribe right now, because what we are covering today is going to go deeper than most space content goes, and you will want to be here for everything that follows. Let us start with the physics. Because before we can ask whether Earth is being observed, we need to understand what observation across interstellar distances actually means and whether it is physically possible. The answer is yes. Unambiguously, demonstrably, already confirmed by our own technology. Yes. Here is the evidence for that in the most direct terms possible. The Voyager 1 spacecraft was launched in 1977. It is currently more than 23 billion kilometers from Earth, well beyond the boundary of our solar system. In interstellar space, we can still communicate with it. We send it commands and it executes them. It sends back data and we receive it. The signal takes about 22 hours to travel in each direction at the speed of light, but the communication link is functional. A spacecraft the size of a small car, carrying technology from the 1970s, is detectable and communicable across interstellar distances using equipment that humanity built nearly 50 years ago. Now scale that up, not to what we can do now, but to what a civilization, even modestly more advanced than ours, could do. A civilization that has had 1,000 more years of technological development than we have. Or 10,000. Or 1,000,000. The physics does not change. Light travels at the same speed regardless of who is using it. Electromagnetic signals propagate across space regardless of who is sending them. The question is not whether interstellar observation is physically possible. It clearly is. The question is whether anyone is doing it, what they would see, and what evidence of it might look like from our end. To understand what an observer would see when looking at Earth, we need to think carefully about what Earth broadcasts into space. And the answer is considerably more than most people realize. Earth has been emitting detectable electromagnetic signals since the planet formed. Natural radio emissions from lightning, from the interaction of the solar wind with Earth's magnetic field, from volcanic activity. All of these produce radio frequency emissions that propagate outward from Earth at the speed of light in every direction. A sufficiently sensitive instrument anywhere within the observable universe could in principle detect these signals. They would be weak by the time they arrived, attenuated by distance, but they would be there. What changed in the 20th century is the addition of artificial signals to that natural background. In 1901, Guglielmo Marconi made the first transatlantic radio transmission. From that moment, Earth began broadcasting something into space that had never come from this planet before. A signal carrying the unmistakable signature of technology, of intelligence. That signal has been expanding outward at the speed of light ever since. Right now, the sphere of human-generated radio emissions is approximately 120 light-years in radius, centered on Earth. Every star within that sphere has already received our earliest radio transmissions. Every star within roughly 80 light-years has received our early television broadcasts. Every star within 50 light-years has received signals carrying the signatures of radar, of military communications, of the entire electromagnetic fingerprint of an industrialized technological civilization. There are approximately 15,000 star systems within 100 light-years of Earth. Many of those stars have planets. Some of those planets are inhabitable zones. If any of those planets hosts a civilization with radio telescope technology equivalent to what we had in the 1960s, they have already detected our presence. They already know we are here. Let that settle for a moment. This is not speculation. This is physics. The signals have already left. They cannot be recalled. They are out there right now, spreading through space, carrying the information that an intelligent civilization exists at this location in the galaxy. Now, brain twist family, here is where the question gets genuinely interesting. Because observation is not a passive one-way process. If someone is observing Earth, the physics of that observation leaves traces that we might be able to detect. And some of those traces look very much like things we have already seen. Let us talk about what an advanced civilization would actually want to observe about Earth, and how they would go about doing it. The first and most obvious observational target is the electromagnetic spectrum. A civilization monitoring Earth would record every signal we emit across every frequency. They would analyze our radio transmissions, our television broadcasts, our radar pulses, our mobile phone networks, our satellite communications. From this data alone, they could determine that we are a technological civilization, estimate our population, identify our dominant communication technologies, trace the development of our technical capability over time, and map the geographic distribution of our civilization across the planet's surface. They could do all of this without ever approaching Earth, without ever revealing themselves, without emitting a single signal in our direction. Pure passive observation, receiving the signals we are already broadcasting, analyzing them with whatever intelligence they possess, building a comprehensive picture of what we are and where we are in our development. This is important because it means the absence of detected alien signals does not mean the absence of alien observers. A civilization that is observing but not broadcasting leaves no electromagnetic trace we can detect. Their observation of us would be completely invisible to us, unless we were specifically looking for the physical artifacts of their presence. Their spacecraft, their probes, their instruments in our own solar system. The second observational method available to an advanced civilization is direct astronomical observation. Telescopes. A civilization with telescope technology comparable to what we will have in 20 to 30 years could detect Earth's atmospheric biosignatures from a distance of many light years. They could identify the oxygen-methane disequilibrium that indicates biological activity. They could detect the spectroscopic signature of industrialization in our atmosphere, the presence of compounds like chlorofluorocarbons that do not occur naturally. They could measure the infrared excess from our cities, the excess heat produced by industrial civilization that makes Earth's thermal signature distinguishable from what it would be in a purely natural state. From this data, they could determine not just that Earth has life, but that it has industrial civilization. They could estimate when that civilization developed, roughly how large it is, and potentially assess the trajectory of its development, including whether it is headed toward sustainability or toward the kind of environmental degradation that characterizes a civilization in ecological overshoot. The third observational method is the one that most directly raises the question in our title. Physical probes. Autonomous instruments placed within our solar system, or even within our inner solar system, to conduct close-range observation of Earth and its inhabitants. The physics of this is entirely viable for a civilization, even modestly more advanced than ours. The concept of a self-replicating von Neumann probe, a spacecraft capable of traveling to a target star system, using local resources to manufacture copies of itself, and sending those copies to further star systems, was proposed by mathematician John von Neumann in the 1940s. A civilization that launched a single self-replicating probe could, given enough time, fill the galaxy with observational instruments without any continuous investment of resources after the initial launch. The timescales involved are long, but not impossibly long. A probe traveling at 1% of the speed of light could cross the galaxy in about 10 million years. The galaxy is roughly 10 billion years old. A civilization that launched probes even 500 million years ago could have instruments in every star system in the Milky Way, today with time to spare. Now brain twist family. Here is where the conversation moves from theoretical to observational. Because we have actually found things in our solar system that raise serious scientific questions about whether we are alone in it. Let us start with the most scientifically documented case. The 1977 Rao signal, which we covered in our previous episode as a brief mention. But today I want to give it the full treatment it deserves because the details matter enormously for this specific question. On August 15, 1977, the Big Sur radio telescope at Ohio State University detected a signal lasting 72 seconds. The maximum observation window of the telescope allowed for any single source as Earth rotated. The signal was narrowband, centered near the 1420 MHz hydrogen line frequency that CTI researchers had long identified as the most likely frequency for an intentional interstellar broadcast. It was 30 times stronger than the background noise. It had exactly the characteristics that CTI protocols specified as the profile of a potential extraterrestrial transmission. Astronomer Jerry Emmons circled the data on the printout and wrote one word in the margin: wow. What is less commonly discussed about the wow signal is the specific astronomical context of where it came from. The signal originated from the direction of the constellation Sagittarius, from a region of sky where there were no known natural radio sources capable of producing a signal with those characteristics. The sky survey had been running for months. That specific region had been scanned multiple times before, and after the detection without producing a similar signal, multiple subsequent searches have pointed instruments at the same region of sky, at the same frequency, with greater sensitivity, than the original Big Air telescope. None have detected the signal again. In 2016, astronomer Antonio Paris published a paper proposing that the signal might have been produced by hydrogen gas surrounding a comet passing through that region of sky. The proposal received significant media attention, but was met with considerable skepticism from researchers who had studied the original data. The comets proposed as candidates were subsequently observed directly and did not produce signals with the characteristics of the WOW signal when observed under similar conditions. The current scientific status is unresolved. The WOW signal remains the strongest candidate for a potentially artificial signal ever detected in 65 years of SETI research, and it has never been satisfactorily explained by any natural mechanism. Whether it was a single transmission from a source that does not broadcast continuously, a signal from a probe at a specific orbital position that has since moved, or something else entirely, we cannot say. What we can say is that it happened, that it fits the profile of what we were looking for, and that it has never been explained away to the satisfaction of everyone who has studied it carefully. Now let us move to something considerably more recent and considerably more officially acknowledged: the UAP phenomenon, and what the government record actually shows when you read it carefully. For most of the 20th century, reports of unidentified aerial phenomena were treated by official institutions as either misidentifications of natural phenomena, classified human technology, or the province of enthusiasts who were not to be taken seriously by mainstream science. The social and professional stigma around taking these reports seriously was real and had practical consequences for the quality of data collected and the rigor of investigation applied. That changed quietly but definitively beginning around 2017. In December 2017, the New York Times published an investigation revealing the existence of a previously classified program within the U.S. Department of Defense called the Advanced Aerospace Threat Identification Program. The program had operated from 2007 to 2012 with a budget of $22 million. The Times story included 3 videos recorded by U.S. Navy aircraft showing aerial objects with flight characteristics that could not be explained by any known aircraft technology. The videos were subsequently authenticated by the Department of Defense. They were officially released in April 2020. The objects shown in the videos exhibited behaviors that serious aerospace engineers found genuinely puzzling. One object appeared to hover motionless against a 120-knot wind before accelerating to speeds that exceeded the capabilities of the sensor system tracking it. Another appeared to rotate in ways inconsistent with any known propulsion system. The sensor data accompanying the videos showed the objects moving in ways that, if taken at face value, would require acceleration rates that would kill any known biological pilot. The official government response was carefully worded, but significant in what it did not say. The Department of Defense confirmed the videos were real. It confirmed that the objects were unidentified. It explicitly did not claim to know what they were. It did not rule out any explanation. In June 2021, the Office of the Director of National Intelligence released a preliminary assessment of unidentified aerial phenomena covering 144 incidents reported by U.S. government sources between 2004 and 2021. The report was able to explain only one of the 144 incidents with high confidence. The remaining 143 were classified as unresolved. The report identified 5 possible explanatory categories for the phenomena: airborne clutter, natural atmospheric phenomena, U.S. government or industry developmental programs, foreign adversary systems, and a 5th category described simply as other. The other category is where the scientific interest lies. The report explicitly acknowledged that some observed phenomena might represent technology or capabilities that are not attributable to any known human source. It did not use the word extraterrestrial, but it did not exclude it either. In 2022, NASA established an independent study team specifically to examine UAP from a scientific perspective. The team included physicists, aerospace engineers, oceanographers, and data scientists. Their final report, released in September 2023, called for better systematic data collection, standardized reporting procedures, and a more rigorous scientific approach to the phenomenon. The report was careful to note that the available data was insufficient to draw conclusions about the nature of the phenomena. But its existence, an official NASA scientific investigation into unidentified aerial phenomena, represents a categorical shift from the institutional position of even 10 years earlier. What does all of this mean scientifically? Brain twist family. I want to be precise here, because precision matters on this topic more than almost any other. The UAP phenomenon does not constitute proof of extraterrestrial observation of Earth. The evidence available in the public record does not establish that conclusion. What it establishes is considerably more limited, but still scientifically significant. It establishes that a subset of aerial observations made by trained military personnel using calibrated instruments cannot be explained by any currently known technology or natural phenomenon. It establishes that the institutional response to this data has shifted from dismissal to serious scientific investigation. And it establishes that the hypothesis space officially under consideration now includes the possibility of non-human technology. That is a significant shift, not a conclusion. A shift in the range of possibilities that serious institutions are willing to investigate openly. Now let us move to a different line of evidence, one that operates at a completely different scale and that receives far less attention in popular coverage than it deserves. The question of anomalous objects in our solar system. We have already discussed Oumuamua in previous episodes. Today I want to look at it specifically through the lens of the observation hypothesis, because several of its properties become considerably more interesting when viewed from that angle. Oumuamua was the first confirmed interstellar object detected passing through our solar system. It was detected in October 2017 by the Pan-STARRS telescope in Hawaii. Its trajectory was unambiguously interstellar, arriving from outside the solar system, passing through and departing. Its approach vector, the direction from which it came, when traced backward, did not point toward any known star system. It came from a direction in space that has no obvious source. Its shape, inferred from the way its brightness varied as it tumbled, was extreme. No known natural solar system object has proportions even approaching the ratio suggested by Oumuamua's light curve data. Natural objects, asteroids, comets, and planetary fragments are irregular, but they are not dramatically elongated or flattened to the degree Oumuamua appeared to be. Its acceleration was anomalous. As it moved away from the Sun, it accelerated faster than gravity could explain. Comets show this kind of non-gravitational acceleration when solar heating causes material to sublimate from their surfaces and the escaping gas acts as a tiny rocket. But Oumuamua showed no outgassing, no coma, no tail, no spectroscopic signature of any kind of material being released. It accelerated without any detectable mechanism for that acceleration. Harvard astronomer A.V. Loeb, who holds the longest tenure of any astronomy department chair in Harvard's history, published a peer-reviewed paper with colleague Shamuel Bialy proposing that one explanation consistent with all the observed data was that Oumuamua was an artificial light sail, a thin sheet of reflective material pushed by solar radiation pressure. Loeb subsequently developed this argument at length in his book Extraterrestrial, published in 2021. The key point that Loeb makes and that I think deserves serious attention, is methodological. The scientific community's response to Oumuamua was to search for natural explanations and to prefer any natural explanation over an artificial one, even when the natural explanations required assumptions about physical processes we have never observed. The nitrogen ice hypothesis, which proposes that Oumuamua was a fragment of a Pluto-like world composed largely of nitrogen ice, requires a mechanism for producing extremely flat or elongated fragments, a source world that we have not identified, and a sublimation rate that produces no detectable spectral signature. All of those are possible, but they are not confirmed. Loeb's argument is that the methodological principle of preferring natural explanations is only valid when we have good prior reason to think natural explanations are more likely. If our prior probability for artificial interstellar objects is essentially zero, we will always find a natural explanation we prefer. But that prior probability of essentially zero is itself an assumption, not a scientific finding. And it is an assumption that becomes harder to justify the more we learn about the potential for advanced civilizations to have existed for long periods in a galaxy this old. A second interstellar object named Borisov was detected in 2019. Unlike Oumuamua, Borisov behaved exactly like a comet. It had a coma. It had a tail. It showed the expected outgassing signature. Its shape was consistent with known cometary objects. It was in every observable way an ordinary comet that happened to have come from outside the solar system. The contrast between Borisov and Oumuamua is scientifically important. Borisov shows us what a natural interstellar object looks like when it passes through our solar system. It looks like a comet. Oumuamua did not look like a comet. It did not behave like a comet. It had properties that natural interstellar objects, as we now understand them from the Borisov comparison, do not have. That contrast does not prove Oumuamua was artificial, but it does make the natural explanation less comfortable than it was before Borisov gave us a genuine control case for comparison. Brain twist family. Let us now move to something that has emerged in the scientific literature over the past decade, and that directly addresses the question of our title. The theoretical framework for what a genuine observation program of Earth would look like from the perspective of an external civilization, and what signatures of that program we might expect to find. This framework comes from researchers at institutions including the CETI Institute, Penn State University, and several European universities who have been developing what they call technosignature research, the search for physical evidence of technology rather than just electromagnetic signals. One specific hypothesis within this framework is what researchers call the Lurker Hypothesis, first formally articulated by astronomer John Billingham and radio astronomer Jill Tarter, and subsequently developed by researchers including James Benford and Duncan Forgan. The hypothesis proposes that an advanced civilization interested in monitoring the development of intelligent life on other worlds might deploy autonomous probes to those solar systems and have those probes maintain a passive watching brief, collecting data without broadcasting for periods potentially lasting millions of years. The hypothesis has specific testable predictions. A monitoring probe in our solar system would most logically be placed at one of the gravitationally stable points called Lagrange points, where the gravitational forces of the Sun and Earth, or the Sun and other planets, combine to create locations where an object can remain in a stable position with minimal fuel expenditure. The Earth, Sun L4 and L5 Lagrange points, located 60 degrees ahead of and behind Earth in its orbit, are particularly stable and have been proposed as logical parking locations for a long-duration monitoring probe. The Earth, Moon L2 point, located directly behind the Moon relative to Earth, would provide a position with continuous line of sight to Earth, while being permanently shielded from Earth's own radio emissions, which would be useful for a probe that wanted to observe Earth without its own instruments being swamped by the planet's electromagnetic output. These locations have not been comprehensively surveyed for artificial objects. Some amateur astronomers have conducted informal searches of the Earth, Moon Lagrange points, and found objects there, though all confirmed objects at these locations are known to be natural quasi-satellites or human-made objects. The comprehensive scientific survey that the Lurker Hypothesis calls for has never been conducted with purpose. Built instruments at the sensitivity levels required to detect a small passive probe. This is not because the scientific community has considered the hypothesis and found it unworkable. It is primarily because until recently, the social and institutional barriers to proposing such a search were prohibitive. A scientist who proposed telescope time for a systematic search of Lagrange points for alien probes would have faced significant professional skepticism. That is changing. The institutional shifts we discussed earlier have opened space for this kind of research to be proposed and funded without the same career risk that would have applied a decade ago. Now let us approach the observation question from a completely different direction. Not from the physics of what an observer could do, but from the biology and anthropology of what observation means, and what it implies about the observer's relationship to the observed. When we ask whether Earth is being observed, we are implicitly asking about the intentions of the observer. Observation can serve very different purposes. A civilization might observe Earth out of scientific curiosity, the same impulse that drives our own astronomical programs. They might observe it to assess whether it represents a resource or a threat. They might observe it as part of a broader program of monitoring developing civilizations. They might observe it with intentions we cannot currently imagine, because those intentions are shaped by a history and a value system completely unlike anything we have experience with. The zoo hypothesis, proposed by MIT astronomer John Ball in 1973, suggests a specific intentional framework for observation. Ball proposed that advanced civilizations might maintain a deliberate policy of non-interference with less developed civilizations, observing but not making contact, similar to the way conservation biologists observe wildlife without interfering with natural behavior. The hypothesis explains the Fermi paradox elegantly. The universe is not empty, it is watched, and the watchers have agreed, for reasons we might not fully comprehend, to maintain their silence until some threshold is crossed. The zoo hypothesis is frustrating scientifically because it is difficult to falsify. If the observers are sufficiently advanced and sufficiently committed to non-interference, they would by definition be undetectable. Any absence of evidence becomes consistent with the hypothesis, because the observers would be hiding the evidence. This makes it difficult to treat as a scientific hypothesis in the strict sense, because a hypothesis that cannot in principle be falsified is not doing the work that scientific hypotheses are supposed to do. But unfalsifiability is not the same as incorrectness. The zoo hypothesis might be true, even if we cannot test it directly. And there are indirect lines of evidence that are at least consistent with it. The UAP phenomenon, particularly the observations that suggest objects with capabilities far beyond current human technology, behaving in ways consistent with observation, rather than aggression or contact, is at least loosely consistent with a monitoring framework in which advanced technology is present, but interaction is deliberately withheld. This is not an argument that UAP observations prove the zoo hypothesis. It is an observation that the pattern of behavior described in the most credible UAP reports, presence without communication, capability without aggression, proximity without contact, is the pattern you would predict if the zoo hypothesis were true. That consistency is not proof, but it is not nothing either. Brain twist family, let us now address the question that I think is genuinely the most important one for this topic. Not whether Earth is being observed, but what it would mean if it is, and how we would know. The question of what it would mean operates on several levels simultaneously. At the scientific level, confirmed evidence of observation would be the most significant discovery in human history, more significant than any previous scientific revolution. It would not just tell us that intelligent life exists elsewhere. It would tell us that that life is sufficiently advanced to be conducting interstellar observation programs. It would tell us that we are not at the frontier of cosmic development, but somewhere in the middle, or toward the bottom of a distribution of civilizations that includes entities of vastly greater age and capability. This context shift would reframe our entire self-understanding as a species. Every question we have about our future, about what humanity might become, about the range of possibilities available to intelligence in the universe, would suddenly have empirical reference points it currently lacks. We would not just be speculating about whether civilizations can survive the nuclear age or the AI transition. We would have examples, potentially many examples, of civilizations that had already faced those transitions, with outcomes we might be able to study. At the psychological level, the implications are more complex and less predictable. Human societies have consistently underestimated their capacity to process paradigm-shifting information, and consistently overestimated the degree of psychological disruption that such information produces. When Copernicus proposed that Earth was not the center of the solar system, the long-term response was scientific and cultural enrichment, not collapse. When Darwin proposed that humans shared common ancestry with other animals, the long-term response was a richer understanding of life's history, not societal breakdown. Both of those transitions took time and were contested, but they were processed. The confirmation of extraterrestrial observation would be a larger transition than either of those. But the evidence from history is that human cognitive and cultural systems are more robust than they are given credit for. The most likely long-term response to confirmed extraterrestrial contact would not be panic, but a profound redirection of human attention and resources toward understanding the nature and intentions of the observers. At the political and security level, the implications depend entirely on what the observation implies about intention. A purely passive scientific observation program poses no security threat by definition. An observation program that is a precursor to some kind of intervention, positive or negative, is a different matter entirely. And an observation program conducted by a civilization whose intentions we cannot determine is exactly the kind of ambiguous situation that human political and security institutions are least well equipped to process rationally. This is one of the genuine, practical challenges of the observation hypothesis. Even if we had strong evidence that Earth was being observed, the response would depend entirely on assessments of intent that we might not be able to make with any confidence. And the history of human responses to ambiguous perceived threats is not uniformly reassuring. So we have established the physics of interstellar observation and confirmed it is not just possible, but already demonstrated by our own technology. We have walked through the electromagnetic fingerprint Earth broadcasts into space every second of every day. We have examined the institutional shifts in how governments and scientific bodies are treating the question of unidentified phenomena. We have looked at specific anomalies in the scientific record that resist easy explanation, and we have explored the theoretical frameworks researchers are developing to think rigorously about what an observation program would look like and where its instruments might be hiding. Now I want to shift the focus, because everything we have covered so far has been about the evidence side of the question, about what we have seen and what we have not been able to explain. The second half of this conversation is going to be about the learning side, about what the observation hypothesis teaches us when we take it seriously as a scientific and educational framework, about the specific fields of knowledge it opens up, about what understanding this question deeply requires us to understand about physics, biology, astronomy, history, and the nature of intelligence itself. Because here is something I genuinely believe about this topic: whether or not Earth is currently being observed. The serious scientific engagement with that question is one of the most comprehensive educations in how the universe actually works that you can get. Every piece of physics we need to understand the observation hypothesis is real physics. Every piece of biology we need to understand what makes Earth observable is real biology. Every piece of history we need to understand the institutional response to this question is real history. The question itself is a lens through which an enormous amount of genuine science becomes suddenly vivid and necessary. That is what we are going to do in this second half. Learn deeply and specifically. Let us start with something that is absolutely fundamental to understanding how any civilization could observe Earth from interstellar distances. And that is one of the most beautiful and counterintuitive ideas in all of physics. The fact that when you look at something distant, you are looking into the past. Light travels at approximately 299,792 kilometers per second. That is fast by any human standard. Light can circle the Earth 7.5 times in a single second. But on cosmic scales, it is not instantaneous. It takes time. And the time it takes carries profound consequences for what observation across interstellar distances actually means. When you look at the moon, you are seeing it as it was about 1.3 seconds ago. That is the time light takes to travel from the moon's surface to your eyes. When you look at the sun, you are seeing it as it was about 8 minutes and 20 seconds ago. If the sun were to suddenly disappear right now, you would not know for 8 minutes and 20 seconds. You would continue to feel its warmth and see its light for that entire interval, experiencing a sun that had already ceased to exist. When you look at the nearest star system, Alpha Centauri, you are seeing it as it was 4.24 years ago. When you look at the Andromeda Galaxy, the nearest large galaxy to our own, you are seeing it as it was 2.5 million years ago. The light entering your eyes from Andromeda left that galaxy when our ancestors were early Homo species, before modern humans existed, before language, before fire was controlled, before anything we would recognize as civilization had appeared on Earth. This principle, that looking at distant objects means looking at them as they were in the past, is not a quirk or an approximation. It is a fundamental feature of how the universe is structured. The speed of light is a universal constant, the same everywhere in the universe for all observers regardless of their motion. This is one of the foundational insights of Einstein's special theory of relativity, published in 1905, and it has been confirmed by every precision experiment conducted in the century since. Now apply this to the observation question directly. If a civilization 100 light years from Earth is observing us right now, what are they seeing? They are not seeing us as we are today. They are seeing Earth as it was 100 years ago. They are watching the early 20th century. They might be watching the First World War. They are certainly seeing a planet whose radio emissions are just beginning, whose technological civilization is in its early industrial phase, whose electromagnetic signature is just starting to become distinguishable from natural background noise. They cannot see our present. They are watching our past. Similarly, if we wanted to observe them, any signal we sent to them would take 100 years to arrive. Their response, if they chose to respond, would take another 100 years to reach us. A two-way communication exchange would take at minimum 200 years per round trip. For a civilization 1,000 light years away, 2,000 years per exchange. For a civilization at the other side of the galaxy, 200,000 years. This is one of the most educationally important aspects of the observation question, because it completely reframes what interstellar observation means. It is not like watching a live video feed. It is like receiving a letter that was written a century or a millennium ago. The civilization you are observing may have changed dramatically, may have ceased to exist, may have become something unrecognizable from the version you are watching, all while your light-speed limited observation is still showing you their ancient past. For an observer watching Earth today from 65 million light-years away, they would be receiving light that left Earth 65 million years ago. They would be watching the extinction of the dinosaurs in real time. Earth, to them, would appear to be a world dominated by enormous reptiles with no sign of anything resembling intelligent life. The planet that exists now, with its technological civilization and its radio emissions and its artificial satellites, would not be visible to them for another 65 million years. This is not a problem that any amount of technological advancement can solve. It is a fundamental consequence of the structure of space-time, and it means that interstellar observation, regardless of who is conducting it, is always observation of the past. The universe does not have a present tense that is shared across distances. It has a series of local presents connected by light-speed delays that become enormous on interstellar scales. Brain twist family. Understanding this deeply changes how you think about the Fermi paradox and about the observation question simultaneously. The silence we observe is not a current silence. It is a silence from the past, the electromagnetic past, as it was when the light now reaching our instruments left its sources. Civilizations that might exist today, whose signals have not yet had time to reach us, are invisible to us not because they are hiding, but because light has not had time to carry the information of their existence to our location. This is called the light travel time problem in cosmology, and it means that our observational window on the universe is fundamentally limited, not just by our instrument sensitivity, but by the speed of light itself. We cannot see the current state of the universe. We can only see a series of historical snapshots, each from a different moment in the past, depending on distance. Now let us talk about something equally fundamental for understanding the observation question: the nature of the electromagnetic spectrum and what different frequencies of radiation tell us about their sources. Most people are familiar with the idea that visible light is just one small portion of a much larger spectrum of electromagnetic radiation. But the full scope of that spectrum and what different parts of it reveal is something worth understanding properly, because it is essential to both the search for observers and the question of what Earth looks like from the outside. The electromagnetic spectrum runs from radio waves at the low-frequency end, through microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays at the high-frequency end. All of these are the same fundamental phenomenon, oscillating electric and magnetic fields, propagating through space at the speed of light. What differs between them is their frequency. How rapidly the fields oscillate, and their wavelength, the physical distance between successive peaks of the oscillation. Higher frequency means shorter wavelength and more energy per photon. Radio waves, at the low frequency end of the spectrum, have wavelengths ranging from about a millimeter to hundreds of kilometers. They pass through most materials that block visible light, including clouds, dust, and the walls of most buildings. This is why radio telescopes can observe the universe through conditions that would be opaque to optical telescopes. It is also why our radio emissions propagate through the interstellar medium relatively unimpeded, making them the primary electromagnetic signature of our civilization detectable at interstellar distances. Infrared radiation, with wavelengths just longer than visible red light, is emitted by everything with a temperature above absolute zero. The amount and spectrum of infrared emission depends on the temperature of the emitting object. Earth emits infrared radiation corresponding to its average surface temperature of roughly 288 Kelvin. A planet with an industrial civilization emits slightly more infrared than an otherwise identical planet without one, because the waste heat from industrial and technological processes adds to the planet's overall thermal output. This excess infrared emission is one of the technosignatures that advanced telescopes might use to identify technological civilizations from a distance. It is subtle. The excess from Earth's current civilization is small compared to the total thermal emission of the planet. But a more advanced civilization, harvesting significantly larger amounts of energy, would produce a more pronounced thermal anomaly that would be more easily detectable. Visible light carries information about the reflectivity and color of surfaces. Earth seen in visible light shows the characteristic blue color of its oceans, the white of clouds, the brown and green of land surfaces. A planet with a large urban infrastructure might show a slightly altered visible spectrum from artificial materials covering natural surfaces. Cities seen from orbit have a characteristic reflectivity that differs from the natural terrain they replace. X-rays and gamma rays are produced by the most energetic processes in the universe, including nuclear reactions, the accretion of matter onto black holes, and the collision of neutron stars. They are also produced at much lower levels by certain human technologies, including medical imaging equipment and some industrial instruments. The contribution of human technology to Earth's X-ray and gamma ray signature is currently negligible compared to natural sources. But a civilization with significantly more advanced nuclear technology might produce a detectable signature in these frequencies. Understanding the full electromagnetic spectrum is not just relevant to the observation question. It is foundational to all of modern astronomy and astrophysics. Every major discovery in cosmology over the past century has depended on our ability to observe the universe across multiple frequencies simultaneously. The detection of cosmic microwave background radiation, the discovery of pulsars, the identification of black holes, the detection of gravitational waves, all of these required understanding the physics of electromagnetic radiation at different frequencies and developing instruments capable of detecting it. Brain twist family. Let us now go deep into something that is directly relevant to whether Earth could be identified as inhabited from interstellar distances. Atmospheric chemistry and the concept of chemical disequilibrium as a biosignature. We touched on this in our previous episode about the search for aliens. But today I want to give it the full scientific treatment it deserves, because it is one of the most elegant ideas in astrobiology, and one of the most important for understanding what makes Earth detectable as a living world. The basic concept is straightforward. Chemistry tends toward equilibrium. If you mix reactive chemicals together and leave them alone long enough, They will react until they reach a stable state where no further reactions are energetically favorable. This is thermodynamic equilibrium. It is the natural resting state of chemistry. Life is, among other things, a machine for maintaining chemical disequilibrium. Living organisms continuously drive chemical reactions away from equilibrium by using energy, primarily from sunlight or from chemical gradients, to maintain concentrations of molecules that would not exist in an equilibrium state. This is not a trivial point. It is one of the fundamental ways in which living systems are physically distinguishable from non-living ones. Earth's atmosphere is in dramatic chemical disequilibrium. It contains both oxygen and methane simultaneously. These two gases react with each other, in the absence of any process continuously producing both. They would react until one or both were consumed, and the atmosphere reached a stable state containing neither at significant concentrations. The fact that both are present, and have been present for hundreds of millions of years, tells you immediately that something is continuously producing both. That something is biology. Oxygen in Earth's atmosphere is produced by photosynthesis, the process by which plants, algae, and cyanobacteria use sunlight to convert carbon dioxide and water into organic compounds and oxygen. Without photosynthesis continuously replenishing atmospheric oxygen, it would react with surface rocks and other atmospheric constituents and be removed from the atmosphere within a few million years. Earth's oxygen-rich atmosphere is not a geochemical feature. It is a biological feature. It is the accumulated waste product of billions of years of photosynthetic life. Methane in Earth's atmosphere is produced by methanogenic archaea, ancient single-celled organisms that live in environments without oxygen, including waterlogged soils, the digestive systems of ruminant animals, and the sediments of lakes and oceans. Without biology continuously producing it, methane would be oxidized and removed from the atmosphere within roughly a decade. The simultaneous presence of both oxygen and methane in Earth's atmosphere at detectable levels is an unmistakable chemical signature of biological activity. Any civilization with a telescope capable of performing spectroscopic analysis of Earth's atmosphere from interstellar distances would be able to detect this disequilibrium. They would know with high confidence that Earth hosts life, not intelligent life necessarily, not technological life, but life, active, ongoing, producing chemistry. This has a direct implication for the observation question that I want to make explicit. Earth has been chemically detectable as a living world for at least 2.4 billion years, since the Great Oxidation event when photosynthetic bacteria first began producing oxygen in quantities sufficient to accumulate in the atmosphere. Any civilization that has been watching the solar system for the past 2 billion years would have seen Earth's atmospheric chemistry change from a reducing atmosphere to an oxidizing one, a change that is unambiguous evidence of a biosphere fundamentally transforming its planet's chemistry. That is not subtle. That is a planetary scale advertisement of biological activity broadcast in infrared and ultraviolet wavelengths that propagate across interstellar distances for 2 billion years. More recently, roughly 200 years ago, Earth's atmospheric chemistry began changing in a new way. The Industrial Revolution introduced carbon dioxide into the atmosphere at rates and in concentrations that have no geological precedent in Earth's recent history. The isotopic signature of that carbon dioxide, its ratio of carbon-12 to carbon-13 isotopes, is distinctive. It matches the isotopic signature of fossil fuels, ancient biological material that was sequestered underground for hundreds of millions of years and is now being combusted and returned to the atmosphere. An observer analyzing Earth's atmospheric spectrum with sufficient precision would see this isotopic shift. They would see an atmosphere transitioning in ways that natural processes cannot explain. They would see the chemical fingerprint of an industrial civilization burning through geological carbon reserves. They might also detect trace amounts of synthetic compounds, chlorofluorocarbons, sulfur hexafluoride, perfluorocarbons. Chemicals that have no natural production pathway and exist in Earth's atmosphere solely because of human industrial activity. This is the chemical portrait of Earth that an external observer would paint from spectroscopic data alone. A planet with ancient and robust biological activity that, within the last 2 centuries in a 4.5 billion year history, began rapidly altering its atmospheric chemistry in ways consistent with the emergence of industrial technology. Now, brain twist family. Let us bring together everything we have covered and ask the integrative question. What would an observer's complete scientific picture of Earth look like right now, assembled from all available information across all observational channels? They would know from atmospheric chemistry that Earth has a biosphere, has had one for billions of years, and has recently developed industrial technology. They would know from radio emissions that the industrial civilization is technologically sophisticated, capable of broadcasting across a wide range of frequencies, and appears to be in a phase of rapid technological development. They would know from thermal infrared emissions that the civilization is producing waste heat at a rate consistent with a global industrial economy. They would know from Earth's orbital dynamics and the gravitational perturbations of other solar system bodies that the planet has a large moon, a stable axial tilt, and a protective gas giant in the outer solar system, all factors that would influence the long-term stability of the biosphere. If they had been watching for long enough, they would have seen the biological evolution of the planet from its earliest microbial forms, through the Cambrian explosion, through the age of dinosaurs, through the mass extinction events that punctuated its history, and through the remarkable recent emergence of a technological species in what is, in geological terms, essentially the blink of an eye. They would have a far more complete scientific picture of Earth and its history than we have of any other planet, because they would have had billions of years of continuous observation to build it. What they would not know, what they could not know from passive observation alone, is what is happening on Earth right now. They would be watching a version of Earth from the past, the distance-dependent past, potentially decades or centuries or millennia, behind the present moment. They might be watching us send our first radio transmissions. They might be watching a version of Earth that does not yet know they are watching. This is the strange and somewhat vertiginous reality of interstellar observation. The observer and the observed are both seeing the other's past, not their present. Observation at cosmic distances is always historical. The present moment on Earth exists only for us, and only now. Let us now talk about something that I think is one of the most intellectually important ideas for understanding this question. The concept of the cosmic perspective, and what it genuinely means for how we understand our situation. The cosmic perspective is a phrase that gets used casually and somewhat sentimentally in popular science. But when you actually work through what it means with precision, it is one of the most practically useful intellectual frameworks available. Consider what Earth looks like from the perspective of the outer solar system. In 1990, as Voyager 1 was leaving the solar system, astronomer Carl Sagan convinced NASA to turn the spacecraft's camera back toward the inner solar system for one last photograph. The resulting image, taken from a distance of about 6 billion kilometers, showed Earth as a pale blue dot, a point of light less than a pixel in size, suspended in a beam of scattered sunlight against the backdrop of space. Sagan wrote about this image in terms that have become some of the most widely quoted words in the history of science. He described Earth as a mote of dust suspended in a sunbeam. He noted that every human who had ever lived, every king and peasant, every creator and destroyer of civilization, every young couple in love, every mother and father, every hopeful child, every inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species had lived out their lives on this pale blue dot. This is not just poetic. It is a scientific observation with direct implications for the observation question. From the perspective of a distant observer, Earth is not a world of nations and cultures, and histories and conflicts. It is a point of light with an interesting atmospheric spectrum. The entire drama of human civilization, all of our wars and art and science, and love and cruelty and achievement, is invisible to anyone observing from outside the solar system. What is visible is chemistry, physics, energy budgets, electromagnetic signatures. This is not diminishing. It is clarifying. It tells us something important about what we actually are at a physical level, independent of our self, narratives and our cultural frameworks. We are a biochemical process running on a rocky planet, powered by a yellow star, emitting characteristic electromagnetic signatures into space, altering the chemistry of our atmosphere at a rate that is detectable from interstellar distances. Understanding ourselves at that level of description does not replace the other levels. It does not make human experience less real or human significance less genuine. But it adds a layer of understanding that is essential for thinking clearly about our place in the universe and our potential relationship with whatever else might be out there. Brain twist family, let us now turn to something more speculative, but grounded in genuine scientific reasoning. The question of what an advanced civilization, observing Earth, would be most interested in, and how that interest might manifest in observable behavior. This requires us to think carefully about the motivations of observers, which in turn requires us to think about what remains constant across different kinds of intelligence, and what might vary. Some motivations seem likely to be broadly universal among intelligent civilizations. Scientific curiosity, the drive to understand the physical world and the phenomena within it, appears to be a natural consequence of the kind of cognitive architecture that allows for technology development. Any civilization capable of interstellar observation almost certainly developed by iterating on a feedback loop of observation, hypothesis formation, and experimental testing. That feedback loop is essentially what science is. A civilization that built it to survive is likely to continue using it to understand. Resource assessment also seems likely to be a broadly relevant motivation. Understanding what resources exist in accessible locations, including the biological resources of inhabited planets, is practically useful for any civilization with the capability to access them. This is not necessarily sinister. Cataloging the biodiversity of a distant world has scientific value that is entirely compatible with respectful non-interference. The monitoring of developing civilizations, watching how intelligence emerges and grows, and faces the challenges of technological development, might be particularly valuable scientific data for a civilization interested in understanding the dynamics of intelligence in the universe. Earth, in the current period of its history, is undergoing one of the most consequential transitions a civilization can undergo. The rapid development of artificial intelligence, the confrontation with the environmental consequences of industrialization, and the first tentative steps toward becoming a spacefaring species. These are precisely the kinds of transitions that would be scientifically interesting to observe. If any of these motivations drives the observation of Earth, the behavioral pattern we would predict is exactly the pattern described in the most credible UAP reports. Presence without contact. Observation without interference. Capability that suggests technological superiority combined with behavior that suggests deliberate restraint. This is not proof of anything, but it is a coherent and scientifically grounded framework for interpreting the available data. And having a coherent framework, even a tentative one, is better than having no framework at all, because a framework generates testable predictions, and predictions can be evaluated against evidence. What predictions does the observation hypothesis make that we can actually test? Several. First, if observational probes exist in our solar system, the most logical locations for them are gravitationally stable points that minimize fuel requirements for station keeping. Comprehensive surveys of the Earth, Sun and Earth, Moon Lagrange points with appropriate sensitivity should either find candidates or place meaningful constraints on the hypothesis. Second, if Earth has been observed for a significant period, the observers would have accumulated detailed knowledge of Earth's electromagnetic emissions history. If they chose to respond to our signals, we might expect the response to show knowledge of our electromagnetic history, potentially referencing early broadcasts that we know the timing and content of. Third, if observational technology is present in our solar system, it might leave subtle but detectable traces, gravitational perturbations of small solar system bodies, anomalous infrared signatures, or optical transients that do not match known natural phenomena. Systematic surveys, specifically designed to detect these signatures, have not been comprehensively conducted. Each of these predictions is testable with current or near future technology. The fact that they have not been systematically tested is not scientific evidence against the hypothesis. It is institutional evidence about the priorities and social dynamics of the scientific community, which, as we have discussed, have been shifting in recent years. Now, brain twist family, let us spend some time on what I think is the most educationally rich aspect of this entire question: the intersection of the observation hypothesis with our understanding of time, evolution, and the development of intelligence. We have established that Earth has been chemically detectable as a living world for roughly 2.4 billion years. We have established that electromagnetic evidence of technological civilization has been propagating outward from Earth for about 120 years. These two timescales are separated by a factor of 20 million. The biological phase of Earth's observable history is 20 million times longer than the technological phase. This disparity has profound implications. It means that if any civilization has been observing Earth, the vast majority of their observation time has been watching biology, not technology. They have been watching the slow, patient work of evolution, the emergence and extinction of species, the gradual complexification of life over geological time. They would have watched the dinosaurs emerge and dominate and be destroyed. They would have watched the mammals diversify into the ecological niches vacated by the extinction. They would have watched the primate lineage develop and branch and eventually produce, in the last few 100,000 years, a species that began doing something qualitatively different from everything that had come before. They would have watched us become human. The emergence of technology, of radio emissions, of the electromagnetic fingerprint of civilization, would not have been a surprise to an observer who had been watching long enough. It would have been the next chapter in a story they had been following for billions of years. The story of how chemistry becomes biology, becomes intelligence, becomes technology. They might have seen it before elsewhere. They might have watched this same transition on other worlds in other star systems. They might have a rich comparative data set of how different biological lineages navigate this transition and what the outcomes look like. If that is the case, their observation of Earth right now is not the beginning of their interest in this planet. It is the payoff. The moment when all those billions of years of watching the slow work of evolution finally produces something capable of looking back. That is a remarkable thought, not just philosophically but scientifically. It suggests that the question of whether Earth is being observed is not separable from the question of what we are and how we came to be. Our existence is the reason for the observation, if observation is occurring. Our emergence as a technological species is the event, the transition. That makes this moment in Earth's history significant in a way that the previous 4 billion years were not. At least not from the perspective of a civilization interested in intelligence specifically. Understanding that context requires understanding evolutionary biology, geology, atmospheric science, and the history of life on Earth at a level that goes considerably deeper than most popular science coverage provides. The Cambrian explosion, the Great Oxidation Event, the 5 major mass extinctions, the development of multicellular life, the emergence of nervous systems and complex behavior. Each of these is not just a chapter in Earth's history. Each is a step in the process that produced an observer capable of asking whether it is being observed. Brain twist family. Let us bring everything together now. Everything we have covered today across both halves of this conversation. Because the individual pieces are interesting, but what they add up to is more important than any single piece. We began with the physics of interstellar observation and established that it is not only possible, but already demonstrated. We walked through what Earth broadcasts into space, the full electromagnetic portrait of our civilization and our biosphere that has been propagating outward for decades, and in some cases billions of years. We examined the institutional acknowledgments that have quietly shifted the conversation from speculation to serious investigation. We looked at specific anomalies in the scientific record that honest assessment cannot fully explain away. We then went deeper into the educational framework. We explored the light travel time principle and what it means for how observation across cosmic distances actually works. We examined the electromagnetic spectrum and what different frequencies reveal about their sources. We went deep into atmospheric chemistry and biosignatures, and why Earth has been chemically advertising its biological activity for 2 billion years. We looked at what an observer's complete scientific picture of Earth would look like assembled from all available data. We thought carefully about what motivations might drive observation and what behavioral patterns those motivations would predict. What does all of this add up to? It adds up to this. The question of whether Earth is being observed right now is not a fringe question. It is not a question that can be dismissed without engaging with the physics, the chemistry, the astronomy, and the institutional record that bear on it. It is a question that sits at the intersection of some of the most important and best established science we have, and that generates genuine testable predictions that have not been comprehensively investigated. It might be that Earth is not currently being observed. The universe might be sufficiently empty of advanced civilizations that no one has yet developed the capability to monitor us, or that the civilizations capable of doing so are too distant for their observation to have reached us yet, or that the filter is real and most civilizations do not survive long enough to develop interstellar observation programs. Any of those might be true. But if we want to know which is actually true, we need to take the question seriously enough to investigate it properly. We need comprehensive surveys of the Lagrange points. We need systematic technosignature programs. We need better standardized data collection on aerial and space-based anomalies. We need the institutional frameworks that allow scientists to pursue these questions without professional penalty. Those frameworks are developing. The telescopes are improving. The data is accumulating. We are genuinely closer to an answer than any previous generation has been. Not because the question has gotten easier, but because the tools for addressing it have gotten dramatically better. There is something else worth sitting with as we close. The act of asking whether we are being observed is itself the most compelling evidence that we are worth observing. A species that has developed the physics to understand light travel time, the chemistry to understand biosignatures, the astronomy to build instruments sensitive enough to detect planets around distant stars, and the philosophical capacity to ask whether anything out there is watching, is a species that has crossed a threshold. It is doing the same thing that any sufficiently advanced civilization would do when it looked out at the universe. It is asking what else is there, and how would we know? If there is anyone watching, they are watching a species in the process of becoming aware of its own cosmic situation. They are watching the moment when the chemistry and biology and evolution of this particular planet produced something that could look back. That moment, right now, in the full arc of Earth's 4.5 billion year history, is genuinely unprecedented. The pale blue dot has learned to wonder about itself. Whether anyone else is watching that wonder unfold, we cannot yet say with certainty. But the evidence that takes the question seriously, the physics that makes it possible, the anomalies that keep the question open, the institutions that are finally beginning to investigate it properly, all of that points in the same direction. This is worth looking into. This is worth understanding. This is worth the full depth of scientific attention we can bring to it. Subscribe to Brain Twist so you are here when the answers come. Share this with someone who needs their understanding of the universe expanded. And think about the sky tonight differently than you thought about it yesterday. Because somewhere out there, across distances measured in light years and centuries and millennia, the universe is very old and very large and mostly very quiet. And right here, on this small rocky planet around an unremarkable star, something is looking up and asking questions. That matters. Whatever the answer turns out to be. This has been Brain Twist. Stay curious. Keep learning. The universe rewards the people who pay attention.